This is part 4 of a series on decision trees. In this video, we'll look at regression trees using the ID3 algorithm. In the last video, we looked at the information gain ratio and discussed pruning methods using confidence intervals. And we wrote code to implement a classification model using ID3 algorithm. In this video, let's build an ID3 decision tree for regression tasks. Let's look at how to create a regression tree by splitting nodes using SDR and CV. The original ID3 algorithm was designed exclusively for classification tasks and is not designed for regression with continuous target variables. It can, however, be adapted for regression by replacing its core metric information gain with one suitable for continuous values, such as Standard Deviation Reduction, SDR. Let's look at the dataset below. This dataset has 3 features X and 1 target Y. The features are categorical data, and the target value is continuous numeric data. This is a dataset for regression tasks. Using this dataset, we want to create the following ID3 decision tree. In this example, we first split the Outlook feature, then the temp feature, and finally the windy feature. And the leaf nodes contain the target values. If a test data point belongs to this leaf node, the target value can be predicted as 45, which is the average of 46 and 44. Regression trees basically work this way. Let's compare the classification tree and the regression tree created using the ID3 algorithm. For performance evaluation, classification models use misclassification rate or accuracy, while regression models use mean squared error, MSE, or R-squared score. And for prediction, classification models use majority voting, while regression models use the mean value. In the example on the left, the target value of the test data point was predicted using the mean value. For node splitting criteria, classification models use information gain, etc., while regression models use the Standard Deviation Reduction, SDR. For decision tree pruning, classification models use post-pruning with confidence intervals, while regression models use pre-pruning with early stopping using coefficient of variation, CV. In this video, we'll take a closer look at these features. Now let's look at mean squared error, variance, coefficient of variation, and standard deviation reduction, SDR. As you know, the MSE for the target value Y is calculated as follows. Y is the observed actual target value in the dataset, and Y hat is the value predicted by a model. This difference is the error, and the mean of the squared errors is the MSE. Typically, in a regression tree, the predicted value at a node is the average of the Y values in the node. So in a regression tree, Y hat becomes Y bar, and MSE becomes the variance of the Y values in a node. And the standard deviation of the Y values is as follows. Next, let's compute the mean of the target values y at the root node before splitting this dataset. The mean of the target y values is 39.79. This is the initial prediction from the model. If we calculate the standard deviation of the target y values at the root node, we get 9.32. Next, let's calculate the coefficient of variation, CV. In probability theory and statistics, the coefficient of variation, also known as normalized root mean square deviation and relative standard deviation, is a standardized measure of dispersion of a probability distribution. The coefficient of variation is defined as the standard deviation divided by the mean. In this example, the CV value at the root node is 0.234. At each node in the regression tree, the mean and standard deviation are calculated, but the average size of the data points contained in each node is different. The coefficient of variation is used to compare probability distributions with different means by normalizing the standard deviation to the mean. This can be used to determine whether it is better to continue splitting a node or to stop splitting it. That is, it can be used as a criterion to stop node splitting. We'll look at this in the last slide. Standard deviation reduction is the difference between the standard deviation of the target y for the parent node and the weighted sum of the standard deviations of the child nodes. We'll look at this in the next slide. This is similar to the information gain used in classification trees. The smaller the standard deviation of the child nodes, the larger the SDR, so it is better to split the node. I use the examples and calculations from this site. Next, let's compute the SDR of each feature to determine which feature is best to split first. First, let's calculate the SDR when splitting the root node into the Outlook feature. The Outlook feature has three categories: rainy, overcast, and sunny. There are 5 data points where the outlook is rainy, 4 data points where it is overcast, and 5 data points where it is sunny. If we calculate the standard deviation at each leaf node, we get the followings. If we calculate the weighted average of these standard deviations, we get 7.66. This is the standard deviation after splitting the root node by the Outlook feature. As calculated in the previous slide, the standard deviation before splitting is 9.32. SDR is the difference in standard deviation before and after the split, so it is 1.66. Next, let's calculate the SDR when splitting the root node into the temp feature. The temp feature has also 3 categories: hot, mild, and cool. There are 4 data points where the temp is hot, 6 data points where it is mild, and 4 data points where it is cool. If we calculate the standard deviation at each leaf node, we get the followings. If we calculate the weighted average of these standard deviations, we get 8.84. This is the standard deviation after splitting the root node by the temp feature. Then the SDR for the temp feature is 0.48. Finally, let's calculate the SDR when splitting the root node into the windy feature. The windy feature has two categories, false and true. There are 8 data points where the windy is false and 6 data points where it is true. If we calculate the standard deviation at each leaf node, we get the followings. If we calculate the weighted average of these standard deviations, we get 9.04. This is the standard deviation after splitting the root node by the windy feature. Then the SDR for the windy feature is 0.28. Here we can see that the SDR for the outlook feature is the largest. Again, the smaller the standard deviation of the child nodes, the larger the SDR. This means that splitting the root node by the outlook feature will result in the smallest standard deviation of its child nodes. Therefore, it is best to first split the root node into the outlook feature. We can see that SDR acts like information gain in the classification tree. Now we split the root node as follows. And by continuing to split each leaf node using SDR in the same way, we can create a regression tree. Next, we use the coefficient of variation to decide whether to split a leaf node or stop splitting. At each leaf node, the mean, standard deviation, and coefficient of variation CV are calculated as follows. The third node has the largest CV at 0.28, while the second node has the smallest CV at 0.08. A small CV means a small normalized standard deviation, indicating that the node contains similar data points. This means that there is no need to split that node any further. Let's set a threshold for CV. For example, let's say the threshold is 0.1. The first node is split into temp or windy features because its CV value is greater than the threshold of 0.1. The second node is no longer split because its CV value is less than the threshold. The third node is also split into temp or windy features because its CV value is greater than the threshold. CV helps prevent overfitting by stopping node splitting. The threshold value, which is a hyperparameter, can be determined through cross-validation. In this video, we looked at how to create a regression tree using SDR and CV. So far, we've looked at ID3 decision trees in 4 videos. From the next video, we will take a closer look at the CART algorithm.